Whenever you tap on an app, have you ever stopped to think about what's really happening inside your phone? We usually imagine the processor is the one brain running the whole show, but the truth is it's not working alone, not even close. Your phone actually has a couple of different brains, you could say, different kinds of memory, and each one has a very specific, very important job.
So, to really get what's going on, let's just pop the back off a high-end smartphone. We're looking at the insides of a Samsung S20 here, which a few engineers were kind enough to take apart for us.
And yeah, of course, right there is the main processor. But look at these two other massive chips sitting right next to it. One of them is a 12GB DRAM chip. That stands for Dynamic Random Access Memory. Think of this as your phone's workspace. Kind of messy, but super fast. The other chip, that's 256 gigs of NAND flash. This is the filing cabinet, the long-term storage where all your photos, apps, and files actually live.
And that right there leads to a fantastic question. If they both just store data, why have two different kinds? Why not just have one giant, super fast chip that does everything? You'd think that would be way simpler, right?
Well, the answer has to do with one of the most fundamental ideas in all of computer science, the memory hierarchy. And really, the best way to picture it is as a pyramid.
See, this whole pyramid thing is all about making trade-offs. It turns out there's no single perfect type of memory that's incredibly fast, absolutely huge, and super cheap all at the same time. That would basically violate the laws of physics and economics. So what engineers do instead is they build a team of specialists that all work together.
At the very, very top of the pyramid, practically welded to the processor itself, are the CPU caches. These are made from something called SRAM, or static RAM. Think of SRAM as the processor's personal assistant. It's unbelievably fast, grabbing data in just a few nanoseconds. But it's also tiny and crazy expensive to make.
Okay, take one step down, and we find the workhorses we saw in that phone. You've got the DRAM, which is the system's main workbench, and then you have NAND flash, which is the tech that powers your solid-state drive, or SSD. These guys are like the middle managers. They strike that critical balance between speed, size, and cost.
And then, all the way down at the wide base of the pyramid, that's where you find your archival storage. We're talking about old-school spinning hard disk drives. They're way slower, for sure, but they give you enormous amounts of space for a really, really low price. It's why massive data centers still rely on them for archival data.
So what this all boils down to is this one fundamental trade-off that you just can't escape. On one side, the faster you want your memory to be, the more it's going to cost for every little bit of data. That super fast SRAM, each bit needs a complex little circuit of 6 transistors. And on the other side, the bigger the memory gets, the slower it tends to be, just because it takes more time to find that one specific piece of data you need in a giant ocean of information.
All right, so now that we've got the pyramid structure down, let's take a closer look and properly meet the key players on this memory team.
This chart really lays it all out. Now, check out that column called volatility. This is super important. Both SRAM and DRAM are volatile. That means they're like a whiteboard. The second you cut the power, poof, everything's gone. That's fine for temporary work, but NAND flash, that's non-volatile. It's like writing in a notebook. It holds onto your data even when the power is off, which is exactly what you want for your photos, right?
Now, this whole elegant pyramid system has worked beautifully for us for decades, but right now it is running smack into a huge problem, a challenge that people in the industry call the memory wall. And this chart just illustrates the issue perfectly. For decades, CPU speed has just been on this explosive, exponential climb. But the speed of our main memory, our DRAM, has improved much, much more slowly. It's more of a straight line. So our processors are like these world-class sprinters, ready to go, but they're constantly stuck waiting for the data to get passed to them.
And this bottleneck isn't just about speed, it's also a huge energy crisis. Get this, in a lot of modern computer systems, over 60% of the total power is spent just moving data around, shuttling it back and forth between the memory and the processor. We're literally burning more energy on the commute than we are on the actual work.
So for a long time, the solution was always just make everything smaller, cram more components onto the chip, but we're hitting the hard physical limits of that flat 2D world. So the industry's really groundbreaking solution is to stop building out and start building up.
The idea is actually pretty simple, but it is revolutionary. Instead of spreading all the memory cells out on a flat piece of silicon, engineers are now stacking hundreds of these layers right on top of each other. Then they connect them with these tiny vertical wires.
They are literally building skyscrapers for data.
And this 3D revolution is happening everywhere you look. 3D NAND is how you can get a multi-terabyte SSD on a chip that's the size of a stick of gum. For gamers, AMD's 3D V-Cache literally glues an extra layer of SRAM cache on top of the processor for a massive performance jump. And then there's high bandwidth memory, or HBM. This stuff is the secret sauce for the AI boom. It stacks DRAM chips right next to a GPU to create this incredibly wide superhighway for data to flow through.
So after going through all of that, what's the big picture here? What's the main takeaway?
Well, it really all comes down to this. Computer memory isn't just one thing. It's this incredibly complex system of compromises and trade-offs. That memory wall is probably the single biggest bottleneck we face today. And these amazing 3D stacking techniques are how engineers are fighting to break through it and keep up with our just insatiable demand for more data.
You know, as one professor at Stanford put it so well, our whole world's obsession with big data, whether it's for training AI or streaming 4K video, it's really fundamentally a challenge of big memory.
Which kind of leaves us with this final big question. We are creating data at an absolutely explosive rate, something we've never seen before. The race to invent and manufacture memory that's fast enough, big enough, and efficient enough to handle all of that, well, it's not just some interesting engineering problem. It might just be one of the greatest technological challenges of our time.